In this video, we want to use Rolle's theorem to prove the mean value theorem. So let's take a look at each of them. Rolle's theorem says that we need a continuous function f that is defined on the closed and bounded interval ab to the reals, that is differentiable on the open interval ab where a is less than b, and where f of a is equal to f of b. And when these conditions are fulfilled, then there is some c in the open interval ab such that f prime of c is equal to 0. Now the mean value theorem, on the other hand, says almost exactly the same thing, except that we leave out this part about f of a being equal to f of b, and then the c that we're finding here gives us this equation. Now before we use this to prove this, let's take a look at how these two equations are related. So we see here an example function for Rolle's theorem. This is a, this is b, and f of a is equal to f of b. And Rolle's theorem told us, of course, that there is some point c where the derivative of f is equal to 0, right? We'll call this point c right here. So what we were saying is that f prime of c is equal to 0. But we could have said that a different way. We could have said, let's look at the line between these 2 points here, a f of a and b f of b, and we want to know the slope of that line. So let's calculate the slope of that line. It would be f of b minus f of a over b minus a, right? And since f of a is equal to f of b, this would be 0, right? In other words, we could put an equal sign here and say that this is what Rolle's theorem says. And that, of course, disregarding this 0 in the middle, is exactly the same thing that the mean value theorem says. In other words, Rolle's theorem is just a special case of the mean value theorem. So let's quickly look at an example of the mean value theorem. Let's say we had, again, a function defined on the closed interval a to b, and we have something like this maybe. Now we take a line from here to here and take the slope of that, which we compute, of course, in the same way as before, f of b minus f of a over b minus a. And the mean value theorem is telling us that we can find a point c, and maybe this is a good example here, we'll call that c, where the slope at that point is exactly parallel to the line that we talked about before between a f of a, so this point here is a f of a, and this point here, which is b f of b. So in other words, this time our c is giving us a point where f prime of c is equal to f of b minus f of a over b minus a, exactly as we see here. So this time we have a point that is supplying us with a function value of the derivative that is equal to the slope of this original line. In other words, the derivative here is parallel to the original line. So we want to use Rolle's theorem, this special version of the mean value theorem, to prove the mean value theorem itself. And this in and of itself is quite interesting. We're using a special case, namely Rolle's theorem, to prove a general case, namely the mean value theorem. Now the other way around would also be possible, right? If we proved the mean value theorem first, then we could say, in particular, this is true when the slope of that line is equal to 0. But now we're going to do it this way. We're using the special to prove the general. So this is how we want to do this. Proof. Let f be a function as described above. In other words, it fulfills all the conditions that we talked about here. It is continuous, it's defined on this interval here, it's differentiable on the open interval, etc. But this need not be the case this time. F of a does not need to be equal to f of b. And at this point, we need a good idea that's not self-evident. Somehow we want to use Rolle's theorem, we know that much, but how can we do it? The good idea that we're going to have here is to use a helping function that we're going to call g. So if we knew, for example, that f of a were equal to f of b, then we could use Rolle's theorem. But since we don't have that information, we don't know that f of a is equal to f of b, and indeed it needn't be equal to f of b, since this is just some arbitrary function, we need to create a function for which that is the case. So let's say this. Let g be the function that is defined from a to b to the reals that sends x to f of x, so just like our function f, but then it adds a certain amount of x to that, which we'll just call a constant r. And we're hoping that by adding a little bit of x in the right way, that we might be able to somehow achieve g of a being equal to g of b. So let's go to the side here and ask the question, when is g of a equal to g of b if we define g in this way here? Okay, well, the first thing we could do is say that would be the case if and only if f of a plus ra were to be equal to f of b plus rb, right? We're just filling in the definition of our helping function g. And we could further rearrange this. Maybe we want to get these f's on the same side, so f of a minus f of b would be equal to rb minus ra. Again, we could rearrange a little bit. We could factor out this r, and indeed we could now divide by r and just solve, or divide by b minus a rather. And we know that b minus a is not equal to 0 because a is less than b. So we have r equals f of a minus f of b over b minus a, right? So now we know what r would have to be equal to so that g of a is indeed equal to g of b. So let's just update our definition here. We'll just write this again. This time we'll say let g be the function that is defined as being from a to b to the reals, where x gets sent to f of x plus f of a minus f of b, I'm just copying what we have right here, over b minus a. So that will solve our problem, because we know that when that is the case, we can even write that here, then we have g of a is equal to g of b. And since that is the case, we can use Rolle's theorem, which means there is some c in AB such that, in our case, this is going to be a g prime of c is going to be equal to 0. So then we can write that. Then there exists c in AB such that g prime of c is equal to 0. Now if that's the case, then we have this very nice result. 0 is equal to g prime of c, and now we can just sub in this here. So that would be, if we take the derivative of g, it's just the derivative of this up here, so that would be f prime of c plus, actually I forgot here, we said we wanted x here. We can't forget that we have an x here. So this x is just going to fall away when we take the derivative, and we'll just end up with this constant here. So we could say f of a minus, what did we have there, f of b over b minus a. Now, if we just subtract this from both sides of the equation, we end up with f prime of c being equal to negative 1, or I'll just put a negative sign, negative f of a minus f of b over, so this negative refers to this entire fraction, b minus a. So now I could distribute this negative sign, and we get f of b minus f of a over b minus a, which is exactly what we wanted to have, right? We have f prime of c on the one side of the equation. On the other side, we have f of b minus f of a divided by b minus a, which is what we had in our original statement of the mean value theorem. So with that, our proof is complete. But let's take a closer look and see if we can't make this a little more elegant. We had this definition here of g. If we just change one sign, we could make that a little more elegant. We have here f of a minus f of b over b minus a, right? This right here. And what it is we're trying to show is f of b minus f of a over b minus a. Almost the same thing. So we could write, instead, we could just copy all of this here. This first bit we could just copy. Let's try that. Oh, that didn't work. Or, you know what, we could just write it. Let g be this function here. And now we're just going to put a minus sign here instead of a plus sign. And then we have f of b minus f of a over b minus a x. Right? So this is just an alternative version that we could use, which I find somewhat more elegant because this is then exactly the thing that we're trying to show later, instead of just being a negative version of it. Now let's take an even closer look, and maybe there's even something even nicer that we could do. So if we wanted to show here that this is indeed the case, because we said here that g of a is equal to g of b, right? Let's say we wanted to show that with this definition here. We want to show that g of a is equal to g of b. Okay, so our definition of g of x is this. It's f of x minus, we'll use the more elegant version here, f of b minus f of a over b minus a x. So what would g of a be? That would be f of a minus f of b minus f of a over b minus a times a, right? So now we would want to multiply through by this a maybe, and we end up with f of a minus a f of b. Let's write it out like this. A f of b minus a f of a over b minus a. Okay, and we're wanting to show that that's the same thing as g of b. And we know that this is true, right? We proved this was true before. But if we wanted to just look at g of a and g of b and see if that they are the same, then we would end up here with f of b minus f of b minus f of a over b minus a. This time we're multiplying by b, right? And we would end up with this here, f of b minus b f of b minus b f of a over b minus a. And even at this point, it's not totally self-evident that these are going to be the same. Now it turns out, if you keep on simplifying here, that these are the same. But could we come up with a definition of this g that would make it very easy to check? And here we need another good idea. So our current definition of g is this, right? We have the closed interval ab going to the reals, where x is sent to this, f of x minus, because we have a somewhat more elegant version than before, f of b minus f of a over b minus a, and we're multiplying that by x, right? That's our current version. But we saw that even with this current version, this more elegant version, it's not so easy to check that g of a is equal to g of b. So the good idea that we could have here is to do this. Instead of multiplying by x, we could multiply by x minus a. Now, let's see how easy it is to check that these are the same. G of a would then be equal to, so I'm just going to sub in a here, f of a minus f of b minus f of a over b minus a times, now here's the crux of the matter, a minus a. So that's 0, right? All that just falls away, and we end up with f of a. Now let's check g of b. We then have, again I'm just subbing in here, f of b minus f of b minus f of a over b minus a, and again here comes the crux of the matter, b minus a. So this just cancels itself out. I end up subtracting f of b minus f of b, and then subtracting the negative of f of a, which just gives me f of a. So because in both cases something cancels out, and I should draw this negative sign perhaps a bit lower so that we can see that this refers to the whole fraction. Then it turns out that since these things cancel, they're both equal to f of a, which makes it very easy to check. So the lesson there is that if we go over to the side and do our algebra and find the r that we need to make the proof work, it still might not be the easiest thing for someone who's checking our proof to see and easily understand. So if I wanted to make a video, for example, showing how to come up with the idea to prove the mean value theorem through Rolle's theorem, then I would use this very first version because it's free of extra thinking, and I can come up with it just by manipulating these symbols. But if I wanted to make a video, for example, about finding an elegant solution to the problem, then I would choose this last solution because of these nice cancellations here. Be that as it may, if I wanted to choose the version with, in my opinion, the best economy of hard work and easy understanding, I would choose the middle one because it didn't cost us much to do. We just had to change a positive sign to a negative sign, and we ended up with a rather elegant version that incorporated the same fraction as we have in our final answer. So there we have a proof of the mean value theorem using Rolle's theorem and a few philosophical musings in addition.